Let's talk about on-street parking. As we all know, on-street parking is a pain. It creates congestion and pollution, and it wastes money and time. This is what on-street parking in the big city of Lyon looks like, where the colors represent the numbers of cars parking at each street portion. Now, for the next 2 minutes and 40 seconds, we're going to answer these two questions. A. Can we predict where these cars are going to park actually, using some analytical formula? And B. Can we then use this to help reduce the search times? To do this, we go simple. Here's a 1D street. Cars coming in from one end at an injection rate I, they're parking, and they're departing at a certain rate capital D. To calculate the spot occupancies, we need just one more thing, the attractiveness, which is simply the probability of a car crossing an unoccupied spot to park there. Using these three ingredients, we can now calculate the probability capital P for a car to park at any spot. This depends on the history of the car. We try this, and it works. Knowing this, and the ODE that defines the dynamics of each spot, we can then calculate the equilibrium occupancies. Well, that's pretty good, but what about a more complicated system? Like this one, for instance. To solve this for the equilibrium occupancies, we need to add two more ingredients. One, wherever there's a fork in the road, we need to specify the relative probabilities of a car turning one way versus the other way. And wherever there's a merge, we need to sum over all the possible paths that a car could have taken. For example, here this car could have come straight up or gone around this loop like this. So we do this and we add the extra terms to the formula and we solve for the occupancy, and it seems to work. So now we have all the ingredients and we want to apply it to a real network like the one I showed you before. Here it is again. This is the business and shopping district of Lyon, separated from the rest of the city by these two rivers, spanned by bridges, which will serve as our injection points I. Having defined this and the departure, we have our first three ingredients. Next, we specify attractiveness, which is shown on this map here, peaked around this location here, which is the Opera House. Finally, defining the transition probabilities using this formula, we can solve it, and we see that it works. The cars park where we expect them to park, and over here the mean error per spot is really small. And so, to our second question, can we use this notion to change where the cars are parking and then reduce the search time? And we see that it can. As we make the attractiveness less and less peaked, we compel the cars to park further and further from their destination, and we reduce the mean search time from 18 minutes to about 3 minutes. Of course, there's a lot that needs to be done still, but for more on that and for questions, please visit my poster session. Thank you.